Okay, so now we need to learn about L'Hopital's rule, and it is a way to evaluate limits, especially when you can't just stick the number into the function to get your answer. So we learned a while ago that you could evaluate limits by factoring, using conjugates, getting common denominators, all that good stuff. But this is just another way to evaluate, which a lot of people sometimes feel is easier. So on these top two examples here, if we try and evaluate just by sticking those numbers into the function, we're going to get 0 divided by 0. Well, we all know you cannot divide by 0. So dividing by 0 cannot be evaluated. So the limit may or may not exist. We don't know. So this is what we call an indeterminate form. In the first case, we can evaluate the limit using old methods. We could just factor this, and then once it's factored, we see that we can cancel the x minus 2, which leaves us with just the simplified function, and if we plug 2 into it, we get 4. Now, just as a side note, remember, this means that this function has a whole at 2 because it had a factor that we can cancel out. But we can't use that on the second one. There's really no way to factor or to simplify. Okay, so here is L'Hopital's rule. It looks horrible, it looks messy, it looks hard, but it's not. All it says is, suppose f and g are differentiable, which just means you can take a derivative of f and g, and you don't want the derivative of g to equal 0. Then all it means is that if you take this limit right here, the limit of f function divided by the g function, it's going to be the same as taking the derivative of the top and the bottom and then evaluating it. All right, with that in mind, let's take a look at the first example that we did by factoring. So we have this problem right here. We're going to take a limit as x approaches 2 of this function. Instead of factoring the top and canceling, we're going to take the derivative of the top, which is what this says, divided by the derivative of the bottom. The derivative of the top then becomes 2x. The derivative of the bottom is 1. And now we can use substitution. We can plug in 2 for x, and we'll get the same answer as we did before. We still get 4. All right, the second example we looked at, we weren't able to solve any way that we knew how from the beginning of the year. So this one, we're going to have to see if we can use L'Hopital's rule. Well, if I stick 1 in for x, I get 0. And if I stick 1 in for x, I get 0. So I do have 0 divided by 0. I do have an indeterminate form, which means that I can use L'Hopital's rule. So I will take the derivative of the top function and the derivative of the bottom function, and that will take me right here. I'll have 1 over x divided by 1. Now can we stick 1 into this function here? And if we do get a real number 1. So therefore, the limit of the original function is now 1. All right, here's another example. We're going to take x as it approaches infinity of e to the x over x. Well, if I stick infinity into e to the x, I will get infinity. And if I stick infinity into here, I will also get infinity. Hopefully you see that this function as x gets large approaches infinity, and this function as x gets large approaches infinity. So infinity over infinity is yet another indeterminate form. So therefore we can use L'Hopital's rule. So we take the derivative of the top, the derivative of the bottom. This is what it ends up being after the derivatives are taken. And then now I can stick infinity into this top function and I just get infinity. Okay, here's another example. Limit as x approaches 0 of 1 minus cosine x divided by x plus x squared. I don't know what that is right off the top of my head. I try substitution. I will stick 0 up into the numerator. When I do that, I will get 0. And if I stick 0 into the denominator, I also get 0. So I have 0 over 0, which means I can use L'Hopital's rule. So we'll come over here. The derivative of the numerator is going to be sine x. The derivative of the denominator is 1 plus 2x. If I stick 0 in here now, I will get 0 over 1, which is a valid real number. It's just going to be 0. Now, if you continue to take a derivative of this, that would be incorrect because this is no longer an indeterminate form. When I stick 0 in, I'm going to get 0 over 1, which is not indeterminate, so we cannot take a derivative of the top and bottom at this point. And down here it just kind of shows if I did take this derivative, it would end up being this, which would give me a limit of 1/2, which is wrong. On the other hand, though, you can apply L'Hopital's rule as many times as necessary as long as the fraction is still indeterminate. So on this fraction, it looks horrible, but if I stick 0 into it, I will get 0 over 0. You can pause if you want and double check it, but it will become 0. It's going to be actually, this step right here is just simplifying this step up before the derivative is taken. So this is raised to the 1/2 instead of the square root, and this is written as 1/2 x instead of x over 2. So if we go down and we take the derivative, here it is, 1/2. We leave the inside alone to the negative 1/2, and then we times by the derivative of the inside, which is just 1 in this case. The derivative of minus 1 is 0. And this derivative here is going to be negative 1/2. The bottom derivative is simple. It's just 2x. If I plug 0 into x on the numerator and on the denominator, I get 0 over 0 again. So that gives me another indeterminate form, which means that I can apply L'Hopital's rule again. So in doing so, we're going to take this derivative, which turns out to be down here, the derivative of the top and the derivative of the bottom. Stop and check if you would like. But now when I plug in 0, I do not get an indeterminate form. I get a number instead. And that number then turns out to be the limit of my original function. All right, so far so good. L'Hopital's rule is pretty straightforward. As long as you have 0 over 0 or infinity over infinity, you can take the derivative of the top and of the bottom and then reevaluate. And you can do that as many times as it applies. But there are some other indeterminate forms that are slightly more difficult, like this one here. We have a limit as x approaches 1 of 1 over natural log of x minus 1 over x minus 1. If I plug 1 into here, the natural log of 1 is 0. I get 1 divided by 0. That's an indeterminate form. This right here is going to head towards infinity. Right here, this fraction here will head towards infinity as x approaches 1. So now we have another indeterminate form, infinity minus infinity. Typically when we have that, we need to rewrite it as a ratio. Or in other words, if we get a common denominator and subtract them. So if we do that, we're going to end up with this right here. So all I did here was get a common denominator. And now I have a function divided by a function, so I can use L'Hopital's rule, hopefully. If I stick 1 in for all these x's, you will find out that we get 0 over 0, which means I can take a derivative of the top and of the bottom. All right, so here is what happens after I take my first derivative. Stop and check if you need to practice taking these derivatives. Once I put 0 into the top and bottom, or actually what I did is get a common denominator down here on the bottom and on the top and flip and multiplied. Then I stick in 1 and I get 0 over 0, so I can take another derivative. Okay, so right here, after taking this derivative and getting 1, and this derivative, getting this, I can plug 1 in, and I'll get an answer of 1/2. Now there was a lot of algebraic work here, so I would highly suggest you go back and kind of take these derivatives on your own, simplify them up, making sure you're getting the same answers that are on the slide here, and then plugging in and making sure you get 1/2. The point of this is to show you the process